Professor Belfrost's science class is back.
Hi, welcome back to my class, and today I will teach you another things about physics. And now we have done our first chapter, and now let's move to the second chapter about kinematics. Kinematics is one of the foundation in physics. There are kinematics, dynamics, mechanics, okay? And kinematics is the first thing that you need to understand. This is the first video on kinematics, so let's pay attention and there's a new spirit on the new chapter. Okay. Okay. So our formal study of physics begin with kinematics, which is defined as the study of motion without considering its causes. Okay. So the word kinematics itself comes from a Greek term meaning motion and it's related to other English words such as cinema, kinesiology, and many more. Okay, so let's first understand the concept of displacement. This is the first concept taught in any class on kinematics. Okay, so in order to describe motion of an object, you must first be able to describe its position. Okay, so displacement comes from position. Okay, actually the first one is position. Okay, the zeroth I think. Okay, the zeroth thing that you need to understand is position of or the coordinate of something. Okay, so position is where it is where the object is at any particular time. Or more precisely, you need to specify its position relative to any convenient reference frame. So, yeah, you can only define something relative to the other things that you taken when that's the reference frame. Okay. For our calculations in physics, most of the time we'll take Earth as the reference frame, but sometimes we can yeah, we can also describe position of an object relative to some stationary objects in that reference frame. Okay. For example, a rocket launch will be described in terms of the position of the rocket with respect to the Earth as a whole, while a professor's position could be described in terms of where it is in relation to the nearby whiteboard, which is stationary to the Earth. Okay. But in other cases, we can also use reference frames that are not stationary but are in motion relative to the Earth. But for this, we'll need another consideration, and this will be more advanced physics. Okay, so for example, we are describing a person movement, motion in an airplane. Then we are using the reference frame as airplane, not the Earth. Okay, which in this case, the airplane is moving. Okay, so if an object moves relative to the reference frame, then the object's position is changing. And this change in position is known as displacement. The word displacement implies that an object has moved or has been displaced. Okay, and the formula is quite simple. Delta x equals xf minus x subscript o. Okay, so delta x, actually anything that comes with delta means that change. Okay, x is just position, actually position in x-axis. Okay, you are free actually to take any other letter. Okay, you can take y for describing when we change in position in y-axis, z for a change in position in z-axis. Even anything actually, you can just take any other letter that best suits you. Okay, but in this case, because we only describe about linear motion x-axis, then we will consider only delta x, xf, okay, and x0. Okay, xf is the final position, x0 is the initial position. Okay, so know that SI unit for displacement in the meter, yeah, but sometimes kilometers, miles, feet, and other units of length are also used. Okay, and you need to convert it to meters to complete the calculation. Okay, because you need to make all the units that involved in a calculation to be the same so you can do the operation. Okay, note that displacement has a direction as well as magnitude, so it is called vector quantity. Okay, so the professor displacement, for example, is 2 meters to the right, and the airline passenger displacement, and this is just example, is 4 meters toward the rear. Okay, so towards something or relative to something or of some degree from some position. Okay, this is very important because it has direction besides having a magnitude. Okay, so in one-dimensional motion, direction can be specified with either a plus or minus sign. When you begin a problem, you should select which direction is positive. Mostly we will take it is right or up to be positive, but actually you're free to select any direction to be positive. Okay, as long as you stick to that convention along way. Okay. Okay, so quick example for you. So say that the professor initial position at 1.5 meter and her final position is at 3.5 meter. Thus, her displacement is x equals 3.5 minus 1.5 equals plus 2.0 meters. Another example, say that airline passenger initial position is at x equals 6.0 meters and his final position is at 2.0 meters, so his displacement is minus 4 or negative 4.0 meters. Okay, so both examples use the convention motion to the right is positive, whereas motion to the left is negative, but you can switch this. Okay, as long as you stick to that convention, you can switch it. Anything will be fine. Okay, so although displacement is described in terms of direction, but another term called distance is not. So distance is defined to be the magnitude or size of displacement between two positions. Okay, note that the distance between two positions is not the same as the distance traveled between them. Distance travel is the total length of the path traveled between two positions, and distance has no direction and thus no sign. For example, the distance of the professor walks is 2 meters, while the distance of the airplane passenger walking inside the aircraft is 4.0 meters. It is important to note that the distance traveled, however, can be greater than the magnitude of the displacement. Okay. For example, the professor could pace back and forth many times, perhaps walking at the distance of 150 meters during a lecture, and yet still end up only 2 meters to the right of her starting point. And in this case, her displacement would be plus 2 meters. And the magnitude of her displacement would be 2 meters, but the distance she traveled have been 150 meters. In kinematics, we nearly always deal with displacement and magnitude of displacement and almost never with distance traveled. One way to think about this is assume you mark the start of the motion and the end of the motion. And the displacement is simply the difference in the position of the two marks and is independent of the path taken in traveling between the two marks. The distance traveled, however, is the total length of the path taken between the two marks. Okay, so I'm sorry, a little break. Okay, because my students. Okay, so what is the difference between distance and displacement? Okay, wherever displacement is defined by both direction and magnitude, distance is only defined by magnitude. Okay, so displacement is an example of vector quantity as I've told you, but distance, okay, on the other hand, is scalar quantity. So a vector is any quantity with both magnitude and direction, while the scalar quantity only have magnitude. Okay, for example, we have velocity, we have force, which both are vectors. Okay, so the direction of a vector in one-dimensional motion is given simply by a plus or minus sign, and it can be represented graphically by arrows. Okay, which will show the length and also the direction of the vector. Okay, but a scalar quantity actually can have minus sign, but it minus sign, negative sign, actually it doesn't show direction, and it show the quantity which is lower than 0. Okay, so in order to describe the direction of a vector quantity, you must designate a coordinate system within the reference frame. And for one-dimensional motion, this is simply just a coordinate system consisting of one-dimensional coordinate line. Okay, for horizontal motion, for example, it is just motion to the right considered positive, motion to the left is considered negative. Okay, for vertical motion, maybe you can take motion up to be positive and motion down to be negative. Just that simple, actually. Okay. Okay. In some cases, however, it's much more convenient to switch the positive and negative direction. I've told you before. Okay. And actually, it does not matter as long as the system is clear and consistent. But once you have assigned a positive direction, start solving a problem, you cannot change it again in the middle of your calculation. Okay, very important. Now let us expand our understanding by covering what time, velocity, and speed. Okay, so the most fundamental physical quantities are defined by how they are measured, and this is about time. Okay, every measurement of time involves something changing in some physical quantity. It may be a number on a digital clock, heartbeat, or the position of the sun in the sky. And in physics, the definition of time is simple. Time is just change or the interval over which change occurs. And it's impossible to know that time has passed unless something has changed. Okay, I'm sorry. Pause. Okay, something went wrong. Okay, so the amount of time change is calibrated by comparing with the standard. Okay, and for SI unit, that is second. Okay, so you can use many things to register the change. Okay, for example, you have using stopwatch, pendulum, or whatever. Okay. So how does time relate to motion? We're usually interested in elapsed time for a particular motion, such as how long it takes an airplane passenger to get to his seat, from his seat to the back of or the rear of the plane. Okay. And to find the elapsed time, we know the time at the beginning and the time at the end of motion. Just subtract these two. Okay. Very simple. And elapsed time, which is denoted as del t, is just the difference between these two and time beginning time. So it brings us with the formula, very simple, self-explanatory, delta t equals tf minus t0. Okay, so we are done with the very basic concept of time, and we'll discuss velocity. Okay, so you know that if you have a large displacement in a small amount of time, then you have a large velocity, and that velocity is the units of distance divided by time, such as, for example, kilometers per hour, miles per hour. Okay, and notice that this definition indicates that velocity is a factor. Okay, factor quantity because displacement is a factor. Okay, it has both magnitude and direction. Okay, there are many units that can describe velocity, but the SI unit is meter per second. Okay. Okay, so the first about velocity is average velocity. Average velocity is just displacement divided by the time of travel. Okay, so v equals delta x divided by uh, delta t. For example, in this example, okay, uh, the displacement is -4, and the elapsed time is 5, so it's about minus 0.8 meter per second. I think I missed something. This is must be the quick example. Okay, and the minus sign here indicates the average velocity of the motion, which is going towards the rear of the plane. Okay, and the average velocity of an object doesn't tell us anything about what happens to it in between the starting time and the ending point. Okay, and it cannot tell us, for example, in the case of the airline passenger, okay, if he has stopped momentarily or back up before he goes to the back of the plane. So to get more detail, we must consider smaller segments of the tree over smaller time intervals. And smaller the time intervals consider emotion, and the more detailed the information we got. Okay, so when we carry this process to its logical conclusion, we are left with an infinitesimally small interval. Over such an interval, the average velocity becomes what called the second term, is instantaneous velocity or the velocity at a specific instant. Okay, so here's the how you measure it. Call there is a equipment tool that called a car speedometer, for example, okay, that can show the magnitude but not direction of instantaneous velocity of the car. Okay, so instantaneous velocity is the average velocity at a specific instant in time or over an infinitesimally small time interval. Okay, so mathematically finding instantaneous velocity, we need to talking about taking a limit or doing some calculus operation, but I think it's not necessary we'll have it in more advanced discussion. Okay. We can find precise values for instantaneous velocity without calculus in most of our circumstances, as will be shown in our next video. Okay. Now let's explain about speed. So in everyday language, actually we just use speed, velocity just interchangeably. But actually this is not true in physics because they have different meanings and you need to distinguish these two concepts. Okay. So one major difference is that speed has no direction. The speed is just scalar quantity. And just as we need to distinguish between instantaneous velocity and average velocity, we also need to distinguish between instantaneous speed and the average speed. Okay, so instantaneous speed is just the magnitude of the instantaneous velocity. For example, suppose that the airline passenger at one instant had an instantaneous velocity of -3 meters per second. Then it means that his instantaneous speed was 310 meters per second. Very simple. You just need to take the absolute value of something. Okay. And for example, that one time during a sailing trip that you instantaneous velocity is 40 kilometers per hour due to north. Okay, so your instantaneous speed at the instant will be just the magnitude. Just take the number 40 kilometers per hour. Okay, easy, right? How about average speed? Average speed is very different from average velocity. You should distinguish these two because it is just like a monster in shape. Okay, so average speed is the distance traveled divided by elapsed time, not displacement. Distance and displacement sometimes can be same, sometimes can be different. So that's why really warn you. I really warn you, not want you, warn you that these two should be taken care. Yeah, you should take care of these two terms and distinguish them. Okay, so you have noted that distance traveled can be greater than magnitude of the displacement, so average speed can be greater than the average velocity, which is displacement divided by time. For example, here is how I can show you. Okay, if you drive to a store and return home in a half an hour, then your car's odometer will show the speed. Okay, it will show you you have uh, traveling by speed of 12 kilometers per hour. So, but this is not the same as the average velocity because the displacement is zero. Then simply your velocity, your average velocity, I mean, that is zero too. Just average speed is not the same as the magnitude of the average velocity. Okay, here's another way to visualize the motion of an object. It is using graph. So a graph is a actually very helpful tool for us, okay, for a physician, okay. So a plot of position or of velocity as a function of time can be very useful. For example, okay, you have doing some trip to the store, you have the record of position, velocity, and speed versus time, and it is displayed as shown in the slide. We're assuming that speed is constant during the trip, which is actually unrealistic. Okay, we will not, okay, will not doing that constant things because we may stop sometimes, we may speed up sometimes, we may slow down sometimes. Okay? But this is just for simplicity's sake. So we'll model it with no stops or change in speed. Okay. Also, we are assuming that the road between the store and the house is perfectly straight line, like shown. Okay. Then you can plot it like this. And I want you to be, this is your first assignment. Please understand what is told by this simple graph. Okay. Okay, now we're done with speed and velocity. The next thing that we need to cover is about acceleration. Okay, so acceleration is factor quantity. Okay, so in everyday conversation, to accelerate always meaning to speed up, and accelerator in a car can in fact cause it to speed up. And the greater the acceleration, actually, the greater the change in velocity over a given time. But actually, the formal definition of acceleration is consistent with these notions, fortunately, but more inclusive. Let's see what it means. Okay, so first is average acceleration. Average acceleration is just the rate at which the velocity changes. So very simple as before, it's just a equals delta v divided by delta t. And because acceleration is velocity in meter per second divided by time in second, then it has a unit of meter per second squared. Okay. And please recall that the velocity is a vector, so this is also a vector. Okay, so for example, if a car turns a corner at a constant speed, it is accelerating because its direction is changing. And the quicker you turn, the greater the acceleration will be. So there's an acceleration when velocity changes, either in magnitude or in direction or both. Okay, but keep in mind that although acceleration is in the direction of the change in velocity, it's not always in the direction of motion. So position, velocity, maybe it'll oppose the velocity and acceleration will goes together, but maybe it's not the same as direction of motion sometimes. Okay, we will see it later from our discussion of problems. Okay, and when an object slows down, its acceleration is opposite to the direction of its motion. This is known as deceleration. So have acceleration, have deceleration. Please note that deceleration always refers to acceleration in the direction opposite to the direction of the velocity. And deceleration always reduce speed. But second term, I want you to pay attention to that deceleration doesn't always mean negative acceleration. I mean that these two concepts is actually not the same. Okay, so negative acceleration is acceleration in the negative direction in the chosen coordinate system, and negative acceleration may or may not be deceleration. It actually uh, depends on the situation. Pay attention to the following figure. I want you to take a screenshot first for the figure. So there are four conditions, four circumstances. There are A, B, C, and D. Okay. So for figure A, see that it's speeding up as it moves to the right, and therefore it has positive acceleration. Okay. For figure B, this curve slowing down as it moves toward the right because it has negative acceleration over coordinate system. Yeah, its acceleration is toward the left, so the car is also decelerating. Okay, because the direction of its acceleration is opposite to its direction of motion. For figure C, this car is moving toward the left but slowing down over time. Therefore, its acceleration is positive in our coordinate system because it is toward the right, but the car is actually decelerating because its acceleration is opposite to its motion. For figure D, this car is speeding up as it moves toward the left, and it has negative acceleration because it is accelerating toward the left. However, because its acceleration is the same direction as the motion of the car, then it is speeding up, not decelerating. So, speeding up, slowing down, accelerating, decelerating, these are not the same. Okay, please don't just use them interchangeably because you'll come to a situation where you terribly switch this and you fail your exam. Okay, very important, very important. Okay, done. So second type of acceleration is called instantaneous acceleration. I need to speed up. Okay, for this discussion. So let me explain. So instantaneous acceleration, the acceleration at a specific instant in time, is obtained by considering infinitesimal, infinite this infinitesimally small interval of time. I'm sorry. So actually, how do we find this infinitesimally small interval of time or the instantaneous acceleration by only using algebra? Actually, this is feasible, and we can just need to take the average of acceleration that is representative for our motion. Let's see. Okay, so for the figure below, it shows the graphs of instantaneous acceleration versus time for two very different motion. See the left figure A. Okay, so the acceleration varies slightly, just slightly, and the average over the entire interval is nearly the same as the instantaneous acceleration at any time. This is sometimes a tongue twister for me. Okay, so in this case, we should treat this motion as if it had constant acceleration equal to the average, which is in this case about if you zoom the picture, you can see it's about 1.8 meters per second square. Okay, but in figure B, the acceleration varies drastically over time, and in such situation, It is better to consider smaller time intervals and choose an average acceleration for each. Okay. For example, we can consider motion for time interval for 0 to 1 to 3 seconds, and separate motion with acceleration of respectively plus 3 and minus 2 meter per second. Perhaps the most important thing to note about is the sign of the answer. So if you're doing calculation later in kinematics, okay. In our chosen coordinate system, plus meaning is the coordinates to the right, minus means it is to the left. This is easy to imagine for displacement and velocity, but actually it is a little tricky for acceleration. Most people will interpret negative acceleration as the slowing of an object, and this was not always the case as I've mentioned before, as a positive acceleration can slow negative velocity if it makes it move to the opposite of the direction. Okay, so the crucial distinction was that the acceleration was in the opposite direction from the velocity. In fact, a negative acceleration can increase a negative velocity. For example, the train moving to the left is sped up by an acceleration to the left too, and in that case, both the velocity and the acceleration are negative. So the plus and minus signs actually just give the direction of the acceleration. Okay? If acceleration has the same sign as the velocity, the object is speeding up, and if the acceleration has the opposite sign as the velocity, then the object is slowing down. Okay, done. So now move to the let's practice section. Okay, only two questions for today. This is just introduction for kinematics. Okay, first one. This is just concept review. Let's check if you understand or not. Okay, so a cyclist rides 3 kilometers west and then turns around and rides 2 kilometers east. So the first is what is this displacement? Second, what distance did they ride? Third, what is the magnitude of the displacement? Okay, so first thing that you need to do, better if you want to do that, I hope that you do that, it is to draw some sketch from the information given in the problem solved. Okay, so after sketch it, you can have a very clear picture. Can have a very clear picture of actually how to solve each of the points. Okay, so first question. Okay, the rider's displacement actually just the difference between the initial the yeah between the final and the initial position. So that's take the change. It is minus 1 kilometers. Okay, it means that you are traveling 1 kilometers to the west. Okay, the second question, I mean, of the first problem, distance travel. What's the distance travel? You travel 3 kilometers to the left, to the west, I mean, and you travel 2 kilometers to the east, okay? You don't need to consider about uh about the direction. You just need to take the absolute value. So 3 and 2 kilometers, that is 5 kilometers, okay? And point C, the magnitude of displacement. I simply 1 kilometer, very simple. Second question, a person's speed can stay the same. They round a corner and change direction. Given this information, is speed a scalar or vector quantity? And explain it. Okay, so speed is a scalar quantity. It doesn't change at all with direction changes. Therefore, it has magnitude only. If it were a vector quantity, it would change as direction changes. Okay. So actually, that's for today. No assignment for today. Okay, you should be very glad because I didn't give you any assignment. Okay, so here's inspiration for a little quote from Mahatma Gandhi. So be the change that you wish to see in the world. Okay, so that's for you today. I hope you always grow and be happy studying. Okay, thanks for watching. Subscribe, give a like, comment, share this video if it's okay for you. And yeah, I'll be back next Tuesday and Thursday. So keep watching, be more thoughtful. Goodbye.